part of Ministry of Arts and Sciences. So IMD also is part of Ministry of Arts and Sciences. There are many other institutes. So we basically work on numerical modeling, you can say computer simulation, which is used for real-time prediction. So we support, we are like the backbone of IMD for the forecast guidance through models. So all these things I am going to show is on the cyberspace what the morning Professor Mitra said. But we use all the satellite data and many other data which I will try to cover. And so I will try to cover basics of some of the models and also show the latest result from our model so that you will get an idea that what data is used, what is the basics of what is the principles, and at the same time where we are going, the most advanced things of touching upon. And I don't have to repeat that how weather and climate plays a very important role for a country like India. Almost all spheres of life is touched upon by weather and climate information. And particularly when you come to India, where the economy is growing and strategically we are in a very changing time, we need this information on weather and climate much more through these prediction models. And this is one slide, very interesting. Britishers were here, and IMD, there was at that time Director General called Glenn. He said India holds the key to unraveling the laws of the atmosphere. To study monsoon, progress of meteorology will be assured. That means we are located in such a, like a laboratory, we are surrounded with mountains, plains, oceans. We have variety of surface, land surface things, and we have so many contrasts. So what is said in 1875, he wrote a letter, and at this slide actually I took from one scientist, Julius Lingo, who is a top scientist in the UK. So she shows this slide wherever she goes to talk on monsoon. And today if you see, it's a very big challenge that can we realistically simulate the monsoon. So what was told in 1875 is today relevant, and you take it from me, all the developed countries like Japan, Europe, US, Australia, they are all thriving to simulate monsoon because it's such a complicated and challenging task. So that's why I will cover some of the slides which will show the simulation of monsoons. I will start with two cases, very recent cases, what the model can do, numerical simulation. Then I will again go to the basics and what data we use, what is the principle of the model. So I have chosen two recent phenomena. One is the cyclone Fani, which was very interesting, and the forecast from the numerical models were very good, which hit Puri in 3rd of May, and the peak intensity was on 2nd. So if I show the rainfall, this is a combination of what Virendra said, GPM plus gauges. So you can monitor by satellite and combination of rain gauge data how the cyclone formed over the sea and gradually came and hit Odisha on 3rd and again moved to Bangladesh and further. So you can see the rainfall from the satellite and how the cyclone came. This is the movie from the observed data, it's not a prediction. Now I will show you, this is the analysis. When I say analysis, it's actually an observation. It's a product of the data assimilation, and you can think this is the initial condition which goes to the numerical model. So this is at 850 millibar, which is 1.5 kilometer. So you can see the date. I tried to show from 24th of April to 3rd May. So how the model initial condition is capturing. So this is not a prediction, but very nicely the model captured the Fani cyclone in the data assimilation system. Now look at forecast. This is forecast. So if you look at the forecast starting from 29th of April, then you see a very good forecast was done. This is the wind at 850 millibar. This is one of the successful recent cyclone forecasting by the numerical model. And if you look at the rainfall forecast also, earlier I showed the observed rainfall. So the forecasted rainfall, it comes and hits Odisha, then it dissipates and moves towards West Bengal and Bangladesh. So very nicely it was predicted 5 days in advance. And this is again to to summarize what I said, this is the analysis on 3rd May, it's like observation, and this is the 500 analysis. The cyclone was seen up to 500 means 5 km. And now we will go to another case of recent western disturbance. What happened on 12th and 13th of May, this December, lot of heavy rainfall was seen over Delhi NCR and north of India. So last one I saw a tropical system. Now I'm coming to a western disturbance. The waves come from here, westerly system, and it gets moisture sometimes from the west, sometimes from the Arabian Sea and Bay of Bengal. So this is the observed rainfall for the western disturbance. Now you see again how the rainfall band in observation comes from the west, and on 12th and 13th. So this is observation, and you see the prediction. So these are the westerly waves which is captured by the model. So you see the date here on 12th and 13th, and this is at 500 millibar because these are dominated by westerly system. So you can see it at 5 km. You can see this very deep trough here on 12th and 13th, which was predicted very nicely in the model. And this is the rainfall prediction again coming from the west. And you remember the observation I showed a few slides earlier, and the forecast also is bringing out very nicely if you see the date 12th and 13th. So this is the capability of the models now, and we have reached a stage where the western disturbance are captured very well in advance. So the 120-hour forecast you see, and even the 144-hour forecast was very well predicted by the model. And this is another case which is February 2019. So you can see this is the observation and 8 days prediction. So these are day 1, 2, 3, 4 up to day 8 in the medium range. The global model predicted very well, and the regional model, which is a high resolution model, I will talk about that. It also predicted very nicely. So these winter predictions are very good by the model compared to the summer. Now coming back, we have got a glimpse of what the model can do. So I will go to the very basics, then again go into what we are having in our center, the latest model. So when we talk about this simulation model, so they are nowadays used, numerical models are used in meteorology to forecast weather, and the process is called numerical weather prediction because it deals with the numbers on a computer. A numerical model is a computer program, so it's now lakhs of lines of code which can simulate the real system, in our case weather, and all these NWP models are based on laws of physics. And these equations are based on those laws which are integrated in time, differential equations. And we need a big computer to simulate this event. So what I showed, these two cases of one cyclone, one western disturbance, they are all output of this computer model called numerical model. And people have been trying this to simulate this from 1904 onward. The concept, because Professor Narasimha today morning he showed this Navier-Stokes equation. This was way back available, but how to solve this equation with some approximation was not available. So people have been trying from 1904. Then there was some attempt by Richardson, and this observation science of modeling became possible, and only during the Second World War it was very much necessary. And in USA, Professor Chabney from MIT and with some of his associates in USA have tried the first numerical weather prediction. And yeah, so around 1950s, people tried to attempt using some very, at that time, whatever computer was available, to make a one-day forecast of very large scale phenomena. Then really in 1954 in USA, there is some joint numerical weather prediction center started, and in 1955 they started issuing forecast for 24 hours, and very simple forecast. Now when we talk about this numerical model, there are different space-time scales. We have global model and regional models, and if you come to much finer scale, what Professor Narasimha was showing in the morning in the cloud scale, they are called CFD models, or very fine scale models are also available. And now from the weather forecasting point of view, what we call short range, and then we have a forecast up to 72 hours. So different type of sophistication of these models are required and medium range is up to 10 days, then extended range we go up, which is up to a season. And to run these models, you need an initial condition. So a lot of input data is required, and so these are the components of a model. You have a governing set of equations, then you have to solve them numerically, and what I showed, the dynamics, the waves are passing, they are mainly model dynamics, but there are fine-scale physical processes which have to be parameterized. They cannot be resolved in the model grid. And finally, you have to do some kind of post-processing in the model. So all these are ingredients of a model. And so what the equations look like? You have conservation of momentum, conservation of mass, conservation of energy, and there is a relationship which is called gas laws, which connects thermodynamics to dynamics. And mathematically, these equations are expressed as system of nonlinear partial differential equations. So it looks like this, and the extra term is the earth rotation, which is called the Fourier's force, which is brought into this Navier-Stokes equation. So these are the basic sets of a numerical model. So we revolve around this model equation, and the task is of this other model is to solve this nonlinear equation numerically on a computer. And what is done in a model, you divide the whole globe into finer grids, then vertically also you slash the atmosphere into many grids. So this is about atmosphere. Similarly, you have the ocean also. So the finer model you want, the computation will increase. So you need bigger and bigger computer if you want to resolve fine scale things. And very important thing, the moment you go to finer scale models, there is something called CFL criteria. It's the time step of the model. You discretize the model into small time steps. So if you see the grid of a model, if you make it fine, your time step becomes small. So it becomes very expensive if you go to fine scale models. So that's why huge supercomputers are required. And again, Professor Narasimha, what is shown in the last slide, we need petaflops of computer to go to very fine scale, which is not possible in coming decade also. Now similarly, vertical resolution, if you want to resolve the phenomena in the vertical, I will show you some slides, you need very high vertical resolution. So it all depends on what computer you have, how much you can resolve. And this is another thing that people prefer a high resolution regional model, but it has its own problems. Suppose there are weather systems passing, which is slightly out of the model domain, like a low pressure system, it will start affecting your boundary and your forecast will get corrupted. So now people prefer high resolution global models only, so that the boundaries are not creating any problem. Now coming to the physical process, what are the physical processes we incorporate in the model? So there are many in real atmosphere, many small scale things are happening. So if I list them, we cannot resolve this small scale phenomena, so we have to parameterize them. So what are these processes like radiation? How the solar radiation is interacting with many components of the Earth system. Then you have surface forces. You go to the surface, these fluxes are exchanged and they provide actually useful moisture, heat fluxes to the boundary layer. Then the turbulence, we are talking about our boundary layer, which is roughly 1.5 kilometer, where the wind is in friction with the surface. There is a boundary layer that's also parameterized because we cannot resolve this turbulence there. Then the clouds, you have seen in the morning how complicated they are. So the model, let's say our model grid is 10 kilometer or 5 kilometer. The clouds are much more small scale, so we have to parameterize them. That means approximate them somehow in the model. So the cumulus convection, and there is gravity waves when the winds interact with the mountain. So all these things are not explicitly resolved in the model. They are all parameterized. So that is one big source of error in the model. Now individually, these are some slides. So each area is like a very important area people are doing research, like how the radiation, solar radiation is working throughout the column of the atmosphere, starting from the surface with the cloud and with the free atmosphere. So there are huge subjects and there are specialists working on this. So I will not go into detail the surface process. What is happening at the surface, how the sensible heat flux, latent heat flux is exchanged, which is the basics of this cloud formation and maintaining the weather systems. That itself is a very huge complex subject. Then we have boundary layer parameterization. So how the mixing. What happens at the surface is mixed with the free atmosphere, because this is the basis of a cloud convection cloud will form or not. How much moisture and heat it is taking through this boundary layer is very important. So this is also parameterized. Then whole cumulus convection, which is again the heat source for the atmosphere. In tropics, the cumulus convection cloud, it maintains the circulation. So if we cannot resolve or maintain this cumulus, on our circulation, what I was showing will go bad. So the dynamics and the cumulus are closely related. The dynamics provides through entrainment and low level convergence how a cloud will be maintained. And at the same thing, the cloud releases a lot of heat which maintains the circulation. So both are actually complementary and both are equally important for tropics. And there are cloud microphysics. Again, within the cloud, how these microphysics, new models which are very high resolution, non-hydrostatics. Some of the microphysics parameters which are measured, they are approximated in the model, not in very great detail, but we need to improve this thing in the model. Now, how all these physical processes interact, they are all interlinked and even linked to the dynamics of the model. So what we do in principle, parameterizing this thing, ignore some of the processes which are very simple because you cannot accommodate them in the model. Or you try to simplify these complex processes I showed and use some assumptions or some empirical formulas from field experiments. You know some relation from the field. You try to put those things in the model. So they are crude approximation. Or you have a lot of observation about cloud radiation. Then statistically you make some kind of model and put them in the model. So they are not resolved in the model but parameterized. So if you look at this, now you have an idea that these numerical models are good for the large scale feature, but where we go wrong? You need a good initial condition. That means you have to define today's atmosphere. So you need enough data and good data assimilation process so that you can forecast ahead. So there are issues there. We are not able to define the initial condition very accurately. The numerical method, how you solve this partial differential equation on a supercomputer. There are many algorithms, but you want very efficient and fast codes to run in a supercomputer. So you do some compromise. So these are the known areas. You can adopt a very sophisticated numerical method, but it consumes a lot of time. Then this physical process, I said, they are all approximated. Then if you use the regional model, the boundary condition at the lateral boundary creates problem. And of course, the lower boundary condition. What is the surface condition, temperature, moisture? They are also very important for solving these large-scale dynamics. So this coming to initial condition, how we prepare the initial condition, which is the today's weather, we can say. So the numerical simulations, what I showed initially, they are mathematically mixed initial boundary value problem. So you need very accurate initial condition. So the process by which you provide the initial value data to the model is known initialization or data assimilation. So we may have lot of data, but how to combine them? It's like a food to the model. How to give in a form so the model can digest it. That's called initialization or data assimilation. This itself is a huge complex science using mathematics and many optimization theories. So these initial conditions are typically provided by a numerical synthesis of available observations. So a variety of observations are available. Virendra showed satellite observation, but we get multiple observations from in situ, then from aircraft, ocean buoys. I will show some of them. So this is part of the WMO's global observing system. So we have to assimilate everything into the model initial condition. And the process is, what we do, we again take help of this model. We make a short forecast of the model. The assumption is the model makes a very good forecast of 6 hours. In 6 hours the error will be less. So we start with the forecast and we have the forecast error statistics, the model particularly dependent on the model. Then we get lot of observation, we know the observation statistics, then we do the data assimilation, combine these two